Hello everyone, we are back with another episode of Computer Vision Talks, and today we have with us Sourav. Sourav is going to talk about his work on SeqNet, which is learning descriptors for sequence-based hierarchical place recognition. The work was accepted at IEEE RAL 2021. He is currently a research lead at Perception and Localization Lab at Center of Robotics. So I'm going to give out a brief introduction. So Dr. Sourav Garg is currently leading the Perception and Localization research theme at the QUT Centre of Robotics as a Postdoctoral Research Fellow. He is a robotic vision enthusiast. His research spans computer vision, robotics, and deep learning, motivated by practical applications that involve a moving camera. He received his PhD from Queensland University of Technology in 2019 while being a part of the Australian Centre of Robotic Vision. His thesis received Executive Dean's Commendation for Outstanding Thesis Award, and his research published in International Journal of Robotics Research won the SAGE QUT Higher Degree Research Student Publication Prize. Okay, that's a lot of achievements. As an active researcher, he regularly publishes in top-tier conferences and journals, including IJRR, RSS, ECCV, CVPR, RAL, ICRA, and IROS. So yeah, that's a lot of research experience and achievements. We are so glad to host you today with us, Sourav. Please go ahead.
Thanks, Shambhavi. So I'll just get started. Hello, everyone. As Shambhavi already introduced, my name is Sourav Garg. I'm a postdoctoral research fellow at QUT Centre for Robotics, that is at Queensland University of Technology, Brisbane, Australia. So today I'll be talking about my recent IEEE RAL paper, SeqNet, Learning Descriptors for Sequence-Based Hierarchical Place Recognition. I'll also briefly give a primer of visual place recognition research, and then touch on some key aspects like contrastive learning and 1D temporal convolutions, which are directly in context of this particular paper. So the main motivation for this research is embodied AI, where we have these robotic agents, which could be autonomous cars, a virtual reality device, or an augmented reality device. So these devices obviously have a moving camera, which means that it makes some of the problems more challenging than what traditional computer vision used to handle. And among these, most of these applications, they require one key capability, that is localization, and that is where visual place recognition research links in. One of the main focuses within these applications is autonomous cars, and I'll give some examples just in that context. So in general, for AI, for example, autonomous cars, detection and tracking is one of the challenging problems, where the task is to detect objects or pedestrians or these cars and other vehicles. So all these dynamic entities in the environment, they need to be detected and tracked so that the robotic agent can take a correct decision and then accordingly act in this environment. Apart from that, there are these static infrastructure items, for example, lanes, traffic lights, traffic signs. So all of this static infrastructure that also needs to be detected and then validated that yes, you did detect it right, and then accordingly a decision will be taken and the robotic agent can act. The third important thing is navigation, because ultimately an autonomous car will have to navigate, and for that it needs to localize itself. So localization means knowing where you are. So for example, so if you guys were able to guess which of these movies they were, so great job. Otherwise, they are all mentioned at the bottom right. So the answer to the question, where am I? So that is what localization tends to do. And visual place recognition is one of the ways to do localization. So with visual place recognition, what we want to do is, if you have seen a place in the past that is represented by, let's say, a collection of images, then when you're revisiting that place, you want to match this particular image with those which you have already seen, and then say that, yes, my current observation matches with what I had seen before, and now I've recognized this place, so I must be at this particular location. So for example, this image is from QUT Brisbane, and then you can locate yourself coarsely within that map, saying that, yes, I'm here. Now, the kind of maps can vary. For example, the standard traditional way is to have 3D maps, where this map is entirely based on geometry, and it could have some topological connections as well. But there are different types of maps which can be used for this task of localization. So it could be a 3D map, which is a metric map. It could be a topological map, or it could be a mixture of both, which is topometric maps. And recently there has been more research into getting semantic maps, where you would also know not just the geometry, but you also know that what each and every other entity is, what an object is within that map. So I'll go through a standard VPR pipeline. So given an environment map, which is a collection of a bunch of images, which is a typical way of doing place recognition. So we have one traverse of the environment where we collect some images from that particular environment. And this is one of the standard benchmark data sets, Oxford robot car, from which these images have been taken. And then you have a query image. So this query image is when you're revisiting that environment, you take one image from that particular place, which you have revisited. And the first thing you have to do is do data representation. So data representation for this query image could be based on local features, where you have some key points defined at different locations. Or it could be a global representation where a single vector is generated from the whole image, for example, using histogram of oriented gradients. So using these key points, local key points or local features, you can represent as a collection. So this collection of key points would be one way of representing, and a global descriptor, a single vector, would be another way. The second thing would be to do data association. So once we have done this representation for the query image and for all the images in the reference database, the second task is to associate the query image with all the reference images. So in this case, we have, local feature matching shown here, where first nearest neighbor search is used for the local descriptors to find the closest matches, closest key point correspondences. And then these key point correspondences are filtered by geometric verification. So other existing methods of doing the same thing is to use, let's say, sum of absolute differences. So that would be just directly comparing two images to do photometric losses.
So if I am correct, sort of, we are just trying to measure the distances.
Yeah, so the key, yes. So what we're trying to do is, given one image, we want to match this image with other images and compute some sort of score, which could be a distance or a similarity measure. And that confidence score would then tell us, if you have a decision threshold on top of that, you can then say that I have matched this image, I have recognized this place.
So confidence score is the sum or the average of all the distances of the key.
Yeah, so for example, for this key point based method, it could be a sum of matching scores. That is also possible. Otherwise, for example, if you use geometric verification, where typically you will have these correspondences, and then you'll try to fit a fine transformation between these images. And then what you get is a kind of error value, which tells you that I was able to fit with this much of error.
Right. Got it. Thanks.
Yeah. So there are few key aspects of visual place recognition. On the left-hand side, these red marked boxes, circles, these are viewpoint invariance and appearance invariance. These two are two of the key challenges which visual place recognition research has been focused on. Then on the right-hand side, we have two different aspects which are more related to the solution of this problem. So for example, how do you do representation and how do you do the association part for place recognition? And then there are these options of using additional modalities. For example, one could use temporal sequences, the temporal information, because obviously robots move, and then if they move, they collect this information within a sequence, or as they keep on moving, you can use that. That sequential information is inherent within most of the robotic problems, especially which are related to mobile robots. And then there are other sensing devices, which is also one of the ubiquitous settings. You would have either LiDAR sensors, or you would have GPS, odometry, or some other sensors mounted as well on a robot. So typically you could use other sensors to make a problem easier. Then using depth or 3D information, that is typically helpful. So that could be based on again, additional sensors, or it could be simply a monocular depth estimation system, which could be used, or either a stereo system. Finally, visual semantics, that is also one of the emerging areas of research where if you have high level information about your current observed scene, for example, you know what different objects are, or if you can reason more about your scene, then you can use that as an additional source of information to improve your performance or to localize better.
Hi, Sourav.
Yeah,
What is
Chandra.
viewpoint invariance?
So I'll come to viewpoint invariance in the next slide, but I'll just give a brief description. So viewpoint invariance would mean that you would want to match the same place. You would want to match the images from the same place, regardless of how you are viewing that particular place. So it could be coming from a different direction or having a different orientation, but looking at the same place.
Okay.
So talking about the appearance, changes in appearance problem. So you can see these 6 images, they all belong to the same place, but the appearance changes significantly. So these belong to Oxford robot car dataset, and they have been captured over several days, over a period of 1 year. And because of change in time of day, for example, day versus night, change in seasons, snow versus no snow, or even sometimes your camera lens being having some sort of dust or anything. So all these problems make your problem visual place recognition problem harder, because you have to match these images regardless of these all changes. Similarly, we have this viewpoint invariance as another target which we want to achieve. Here, the example which I'm using, it's more of an extreme scenario where we want to match images from opposing viewpoints. So in this case, if you, on the left and top left, if you see a car which is going down a road during the daytime, if at the night time it comes back to the same place, but from an opposing direction. So what will happen is the visual overlap between the two observations, it will be very less. So for example, on the right-hand side, you can see these 2 images where you'll see this particular building is still being matched, but rest of the information, which is the points which are far from the camera, they cannot be matched because that part does not overlap. So this is again a hard problem, because if the amount of visual overlap is limited, then there is very less information which you can use to match these 2 images which belong to the same place. So here's a better example. So you can see the red marked area. So these 2 buildings as landmarks. So they are mutually observed in the 2 images, but the green and blue marked regions, these are not the same buildings. So this is what then makes the problem hard, because then you could be cross-matching wrong information, which would mean that your confidence of matching these 2 places will reduce. And this problem becomes even more challenging if your scene appearance also changes. For example, now we are matching from opposing viewpoints, and we're also doing a day versus night kind of scenario. So this makes this problem even further harder when you have both viewpoint and appearance changing significantly. So there is a vast literature for place recognition. So recently, with the advent of CNNs, so off-the-shelf CNN features have been used. They were the first attempt to do place recognition by just using CNN final convolutional tensors to represent an image as a global descriptor. And then these descriptors were used to match images by using cosine distance measure or Euclidean distance measure. And similarly, some other works where different pooling techniques have been used. So given the final convolutional tensor, one could use maximum activations, or like, for example, a MAC vector or a region MAC vector. So again, some sort of patch-based representation could also be used. So in all these cases, these representations, these are again ways of representing your places. This work then evolved into an end-to-end learning system where contrastive learning based methods, for example, NetVLAD or gem pooling. So these methods have been used where the idea is to learn a representation such that images from the same place, they have a closer representation in the latent space, and the distance between 2 images from different places, that distance increases. So generative adversarial networks have also been used. So for example, converting day images to night images. So those kinds of options people have also considered, but then there are some generalization issues there. So apart from using global descriptors, local feature-based methods have also been used. So this is one of the works from Google, I guess, where Delph pipeline was one of the ways to learn end-to-end local features. So not just the local descriptors, but also local key points. So in this way, this was basically done for landmark recognition, but this was also found to be useful for place recognition. So this is the work which uses GANs to translate day images to night images, or rather night images to day images. So at the top, you can see that the local feature matching is not that great when you're considering day and night scenario. But if you can convert the night image into day image, then local feature matching can be used to get better matches. Yet another important aspect which is related to this particular paper, which I'm discussing, is sequence-based techniques. So in sequence-based techniques, one basic idea is to do image matching pairwise. So you have single image descriptors which are matched with between query and reference. So for example, here you have a distance matrix. And in this case, your rows represent different reference images and your columns represent different query images. So here, what we do is we use single image descriptors, compute matching scores between them, and then try to fit a line within that this particular cost matrix. So all these blue points that show that there is a minimum distance, so which means that the confidence is high, and rest of the particles here, all these other squares, they show that this distance is actually higher. So which means that these are not good matches. And we try to find a matching sequence across this diagonal. And this is based on the use of sequential information, because you assume that the order in which you have observed places, that order is going to remain intact. So you're going to get a diagonal here to match places. But one issue which is commonly observed in these sequence-based methods is that there is a camera velocity sensitivity, which means that if the speed at which the robot was moving or the autonomous car was moving during the reference traverse, as compared to when it was moving during the query traverse, that changes. So the change in speed could mean that you won't get a perfect diagonal. So there are sophisticated sequence searching techniques which are available, but one practical solution is to use odometry information. So if you have odometry information, then you can sample your frames with a fixed metric distance. For example, you could use odometry information to sample frames at every, let's say, 2 meters or something. So that would mean that you get a straight diagonal here. So in this case, this diagonal, once you have this diagonal, it makes the problem easier. So you can search sequences rather much easier, in a much easier manner. This is our recent work where we propose sequential descriptors. So the idea, as compared to the previous method, where mainly we were doing sequence score aggregation, which means that we have single image-based descriptors, but we construct that matrix, and then on top of that matrix, we do any kind of sequence matching. But here, what we're trying to do is, instead of having a representation based on single descriptors which are independent, we rather consider a sequence of images and then create a representation out of it. So this method is unsupervised. It has one assumption that there is enough of frame separation between consecutive frames, so that then you can compute a delta between consecutive frames, and then that becomes one unique representation for that particular place. I'll show you a video which kind of gives an idea for why a representation might be a good idea for representing places, especially when using sequences. So here, just to have an idea of the legend, what we're using. So green and red, these two segments, they are two different traverses. So green one is from autumn traverse and red one is from summer traverse. And what we are looking at on the left-hand side, these are 3D embeddings. So once you create a representation vector, single vector for a sequence of images, in this case, we're just using a smooth, like descriptor smoothing to construct a sequential descriptor. So what we're trying to do is we have converted through PCA these descriptors into 3D points. So this is not a GPS coordinate, which we are plotting here. It is actually a 3D embedding rather, which is constructed from the descriptor space. So once I play this video, so as the robot would move in both the traverses, so these are perfectly aligned. So the traverses are aligned, but we'll see that these embeddings, they do not always align with each other. And there is certain gap between these embeddings, which shows that there is an offset which needs to be fixed. So here we go. So at certain places, the offset would increase, but you can see the overall shape kind of remains the same. So this, the shape being the same is what the main idea behind using delta descriptors. Like we want to, by taking the difference, we kind of get rid of that kind of offset between these two embeddings. And, but the representation itself is based on a sequence, which is relatively more helpful than just using a single image descriptor. Some related literature, some more from some other research labs. So this one is a recent work where, again, using contrastive learning, there were 3 different types of representations generated for sequences. So one was based on a fully connected layer, which connects all the images in the sequence. The other one was based on concatenation of these 3 images, like because they were considering 3 images as a place, or maybe probably 5. So given all these images in a sequence, you can either concatenate them, either run a recurrent neural network, or you can run a fully connected layer which connects all these images. So using these 3 different types of representations, they were doing contrastive learning to then learn representations. Similarly, there is some other work which also uses, for example, on the left-hand side, we have binary descriptors. So this one is an unsupervised technique. It uses, it converts images into binary descriptors and then concatenates them. And the one on the top right, this method is bio-inspired. It does a recurrent neural network style embedding and then keeps on searching for correct images in a distance matrix, using this distance matrix. This one, the third one, is a more recent work where both LSTMs and CNNs are used to represent images as well as learn the temporal dynamics. So we have ourselves contributed to this VPR literature as well in last few years. So on the top left, this is the work which we did where we used semantics as an additional modality to improve performance for opposing viewpoints and changing appearance conditions. So using visual semantics and using implicit key point correspondences. So this method tends to work better than many other existing techniques. And then on the right-hand side, we have a fast sequence matching technique. Here, the main idea was to, if you have a very large database, so how we can rapidly find correctly matching places. So in this case, we would consider a 10 million size large reference database and then try to find matches in a very, with a very low latency. The third one is using 3D depth information to create a topometric representation of the environment. Again, this work was targeted to improve place recognition for opposing viewpoint scenarios. This one is a recent CVPR 2021 work where we considered local patches and then created patch net VLAD system out of that, where the idea was to have this global understanding of the scene embedded within the local features themselves. So this method does not require any additional training, but just using a system which is trained for global descriptors for place recognition, we adapted that to work for local patches. And then we use re-ranking, which is a common method in hierarchical place recognition. Using local features, we re-rank the places and then find a final matching place. VPR bench, this is also a very recent work. In this case, we've developed this VPR bench where there are 12 data sets and 10 different techniques. And apart from that, there's significant additional analysis which we have done to find out that there's no single state-of-the-art method, and different methods have their own capabilities, their own characteristics, which we have tried to measure through different analyses. So we do have a question over chat.
Shall I read it out, or Karthik, would you like to unmute and go ahead?
Yeah, so what I was wanted to know is, are you also trying to reduce the offset between the two representations in the video that you were showing? Or if yes, then how you are trying to do that part? Because what I can assume is, if you are trying to reduce the offset between the two representations, then that means that you're in a way trying to get a domain invariant features out of your feature extractor network, right? So if you're doing that, how are you doing that? Can you please share some thoughts about it?
Yes. So in that particular work, what we did was we first of all visualized that, okay, there is this offset, but the shape, if you look at the shape, it would remain roughly the same. So we wanted to just have a handle on that particular shape characteristic. So one very easy way to get that shape was to just, so the way we constructed delta descriptors, so that in some way captures that shape in its definition, because it is like calculating the slope of that, what do you say? So delta descriptors, what we do is we first smooth the signal within a given sequence length, let's say 16 frames or 32 frames, depending on how the frame separation is between consecutive frames. So if it is too low, so you'll need a longer sequence length. So once you have the sequence, you smooth that, which means just doing averaging, and then you compute a delta between consecutive frames. So this gives you a kind of high dimensional edge vector, which itself captures the slope of that vector within that very small segment. So it is like differentiating that vector. So that to some extent captures the shape of that whole sequence. So once you have that kind of shape characteristic embedded within this delta descriptor, so then you don't need to then worry about the offset, because then even if it is from different domain, but you do know that your shape in the high dimensions, it is remaining the same. So that is how we approached that particular problem and came up with that method. I hope that answers your question.
So you're trying to say that even though there is a domain shift, the night and the day,
yeah.
So if you say, you're saying that that shift doesn't matter if the shape is same or at least similar.
Okay. Yeah, so yeah, it is analogous to the fact that some very initial work for place recognition, which considered patch normalized images. So there the idea was that if you normalize your patches locally, then you only have relative change information. So then you could match your day image with the night image. But if you were to directly match them, then obviously there would be a gap in your photometric error. So because your day image would have high intensity, night image would have low intensity, so you can't do that. But if you are normalizing them, so you could actually match them in that way. So a similar idea is what we're using here. So within a sequence, if you just look at these differences, then you'll expect that these differences would remain the same across different domains, so even though the actual values might actually shift.
Okay. Then thank you very much. Yeah.
Yep. No worries. All right. So these are some of the additional works which are all related to place recognition, and we have explored different ways to address different aspects of this problem. And the last one here is SeqNet, which I'm talking about right now. You can, so most of them do have codes available for them. You can look at the GitHub page for using any of these methods or learning more about them. This is yet another recent work where we did a survey on semantics for robotic mapping, perception, and interaction. We also came up with a new taxonomy for using semantics for robotics. And This one does comprise a significant chunk for semantics for place recognition and localization as well. So it could be a good read for anyone interested in using semantics for robotics. This one just got accepted last week. This one is an HCI survey track for 2021. Here we talk about place recognition. We come up with a new definition, which is complementary to or different from what already existed. And we also talk about what is the motivation behind defining like how the place recognition problem should be solved. So the key drivers behind that, and how place recognition relates to different problems like image retrieval, video retrieval, landmark recognition, overlap detection. So for anyone who is starting or even anyone who is an expert, so we tend to disambiguate place recognition from other research problems and define it more in a better way. So this should be a good read for, I hope, many readers. So for SeqNet, the motivation mainly is that there is a research gap where we know that the existing systems have certain limitations, especially when single image-based descriptors are used. They are always computed independently for different images. And then on top of that, one constructs distance metrics, and then sequence matching is done on top of that distance metrics. But the underlying matching scores, they're always computed using single images. So those single images, they do not talk to each other when they're represented through some sort of descriptors. But what we want to do is we want to do a sequence-based representation. So this means that your place representation itself is aware of your information from the past sequence, so from the past whatever robot has observed. So using this kind of sequence-based description, one can then additionally do sequence code aggregation if, as we have done in SeqNet as well, because there's a difference in terms of how you enforce order within your representations. For example, by doing any kind of sequence code aggregation on those distance matrices, one could enforce order rather more strongly. So these methods are still relevant, but using sequential representations, that makes your descriptor, your representation much more robust because it is more informed than a single image descriptor. This is just an overall schematic of what we're trying to do. So given multiple images, a sequence of images from any place during the daytime, that constitutes our reference database. So we have these sequential descriptors and single descriptors per place. And then during the nighttime, we want to match this set of images, which is represented by single descriptors and a sequential descriptor constructed to SeqNet, to then find the correct matches. This part here shows sequence code aggregation because we use a hierarchical pipeline, which I'll explain in more detail shortly. So these are the main components of this proposed framework. And the main idea here is to have that additional sequential information, which could then help in challenging scenarios, for example, matching images from devices from day to night. So one of the key components of SeqNet is using contrastive learning to learn representations. So contrastive learning, there are many different ways of doing this. One of the common ways is to use triplets, where what you do is if you have an anchor here and a positive here, which means for place recognition, it would mean that these two images have been taken from the same place. But there are other images which have been taken from a geographically different place, but the representation vector or that point in that high dimensional space could be sitting somewhere here. So that particular element would be termed as a hard negative, because the distance between, if this was an ideal positive anchor, a positive and anchor, and this was the distance which should be there between an anchor and positive. So no negative should actually be sitting in this red area. So if there is any element which is sitting in this area, then it is referred to as a hard negative. And then there is a margin which we define. So we would want that all the negatives are sitting in this area, which is green. So we would want them to have a certain margin apart from the positive, so that during the test time, no one from this orange area enters the red area, which would be a fail. So the red part is hard negative area. The orange part is a semi-hard negative area where some of the negatives which could still exist there, but it is possible to push them by this margin and throw them in the easy negative area. So once you have all the negatives within this area, then you can say that your solution is converging during the training, and all the positives, there are just positives which are sitting in this circle, no negatives. In terms of equation, this is a max margin loss where you have anchor positive distance, anchor negative distance. So this is a Euclidean distance here. And you want this to have a certain margin. So your anchor, so you want your anchor positive distance plus margin to be greater than, to be less than this particular anchor negative distance. So your negatives should be always be sitting here. So although like contrastive learning has been used in so many different problems, so this is one example for place recognition. Here the loss formulation was a bit different. But this is an example where generalized mean pooling was used for representation, and this particular loss function was defined, which was a contrastive loss. But you can see that the positive pair has this building, which is the same place, and these two, which are the different ones. So you define negatives and positives accordingly. But what we want to do is, instead of using this concept of single images, we want to do it for the sequence of images. So the existing methods would typically try to reduce distance between an anchor and positive. So anchor is orange, positive is green here. So these are images from the same place. So you want to reduce distance between them, and you want to increase distance between the anchor and the negative. But instead, what we want to do is we want to rather have the whole sequence, then the sequence represented by a single representation vector, and that representation vector should reduce distance with the anchor, and same thing for the negatives. So the representation itself should be based on sequences, and then we learn this representation. The sequential descriptor is learned by contrastive loss. The other important thing here is the use of 1D temporal convolutions. So people might be familiar with 2D convolutions, which typically operate in the dual axis of width and height of an image. But here what we have is a single vector of an image, and then we have a sequence. So the axis on which convolutions operate, that is the temporal axis. So here the key idea is the same. You have this input vector, and this is the time axis. So a kernel would be operating in this direction, and then you can compute this element C1 after convolution as W1x1 plus this. Similarly, other elements. On the right-hand side, there's another example for the same thing. So these temporal convolutions, unlike 2D convolutions, the output tensor size would be accordingly changed. So you only have one dimension across through which this convolution is operating. So this is the whole pipeline of our proposed algorithm. I'll go through this one by one. So we have this input query sequence, and what we do in this work is that for each image, we consider a global descriptor, which is not learned. So we can use any existing single image descriptor method, which can be plugged into this whole framework. So these global descriptors, these are computed. For this work, we use two different options. So one was NetVLAD, and that gives us a 4096 dimensional global descriptor. So for each image, one descriptor is computed, and these computations are independent. So for each image, it is independently computed. So once you have these input descriptors, we can then compute a sequential descriptor, which is represented as SLD. L and subscript D, this refers to the length of the sequence, which is used to compute this sequential descriptor. Here, these temporal convolutions are operating in this direction, and this particular vertical axis is the dimension D. So in this case, it is 4096. So this temporal convolution plus bias, this is the first layer. Then there is the second one, which is sequence average pooling. This is analogous to global average pooling, which is typically used, and then you do an average across width and height for an image. Here, the average pooling operates in the temporal axis dimension. So once you do a temporal con with a 3x3 filter, with a 1x3 filter, so you get, without padding, you'll get 3 elements out of this. and those three would be averaged. And then you have L2 normalization. So L2 normalization is a kind of a best practice. So it has been found that for high dimensional vectors, matching them with cosine distance is typically better than using Euclidean distances. And with L2 normalization, your cosine distance becomes proportional to Euclidean distance if your vectors are L2 normalized. So this means if you've done L2 normalization, so your representation points now sit on a unit hypersphere, and by doing Euclidean distance, you are proportionally doing cosine distance based ranking. We do the same thing with the reference database. So here there was a single query sequence. Now we have the whole traverse, and for each of these sequences will have one sequential descriptor defined, and this is done in a continuous manner. So for every image, there is one sequential descriptor defined based on a span of, let's say, 5 frames. So these descriptors are then matched by Euclidean distance, and then we'll use these sequential descriptor based matches to guide our single image descriptor based sequence matching. So here, this is the part where we consider single image based refining of descriptors. So we know that the existing descriptors may not always have their robustness to day versus night kind of conditions. So we retrain single image descriptors by putting a single fully connected layer plus bias and L2 normalization. So there is no temporal convolution here. It's just all the 5 descriptors coming here and independently getting updated to a single learned descriptor again. So these are all independent single descriptors. So these are processed descriptor wise, but that one was processed as a sequence. So same thing is again available for the reference database. So we have a sequential descriptor per place and we have a single descriptor per place. So both are learned for that particular domain. And with the sequential descriptors, what we do is we retrieve top matching candidates. So these top matching candidates, for example, let's say we're considering 3 here, these would then be used in the sequential matching pipeline. So here, now we have come back to doing the sequence score aggregation where single image descriptors are matched in a using this cost matrix or distance matrix. And the best match is obtained based on where you fit the diagonal the best. And then you get your best match. So the main reason why we want to do this kind of hierarchical pipeline is because sequential descriptors themselves do not have that a very strict order. So which means that they may not have the same capability as a sequence score aggregator method would have, but they do have an additional advantage that because the representation itself is informed by a sequence of images, so these representations are robust. So you can still get a very high performance, but by using that as a hypothesis generator, we can then feed in good matches to this part of the pipeline, which then further takes this performance even higher. So we use 4 different data sets for this case. So Oxford robot car day versus night and Brisbane city loop day versus night. So we did the cross city comparison, so train on one city and test on another city for day versus night kind of scenario. And the same thing was done for mapillary street level sequences where different cities, like data from different cities is used. And we train a model on just one and then test on others. So Nordland seasonal variations data set, we use this to test whether if training on a particular set of conditions, can we transfer this to another set of conditions? So for evaluation, this is an important part. And it does have some similarities with how COVID tests work. So you might already know this, but it would make it easier for you to understand how we do that for face recognition or for that matter, any other AI system as well, many others. So you know that if the test detects virus and a patient has virus, so this is a true positive. If your test doesn't detect virus and patient doesn't have virus, it's a true negative, which is great. False positive is that the test detected virus, but there was no virus. And the test detected no virus, but the patient had virus. So this is the most dangerous case, which means the test had failed, which is true, which can happen. So your the ultimate thing to that say is that if you have symptoms, to stay at home. So similarly, we have the case for place recognition, where if the ground truth says the place is same and your retrieval systems, it retrieves the place correctly. So this is a true positive. But in other cases, if there is a mismatch between your what ground truth says and what your prediction is, then the other elements are also defined accordingly. There's a slight change for place recognition, which depends like how do you evaluate. So in our case, what we do is we do not consider false positive or true negatives. We only consider true positives and false negatives, which means that for every query, we know that there does exist a correct match. So the ground truth always have same place. There is no such ground truth where there is a different place. And the prediction has to then tell that for this query, whether it was able to retrieve the same place or not retrieve the same place. So if it fails, then that counts as a negative. So the recall measure is defined here as true positive divided by true positive plus false negatives. We considered few different baselines and ablation studies here. So the main pipeline which we propose is HVPR, which is hierarchical visual place recognition, as I explained before. So there is a sequential descriptor, which is referred to here as S5. And that sequential descriptor to S1 means it guides the single image based sequence score aggregation scheme. So that is the one which we found to work the best or mostly achieve good results. The second one here is SeqNet, which is the sequential descriptor alone. So how good does that perform? So we test that. The other one is we have the single image descriptor. So we know that single image descriptors are not going to perform as good as a sequential descriptor, but in some cases they do. There are some such cases. So we consider SeqNet S1, which is a fine-tuned descriptor as compared to the raw single descriptor. For example, NetVLAD in this case. So this is the raw single descriptor. This is a SeqNet single descriptor, where this one is defined for that particular domain or particular setting. And then plus sequence matching is the sequence score aggregation, where I show you the cost metrics and we do score aggregation over that cost metrics. So that can be defined, that is defined on a single image descriptor. So it could be defined on SeqNet S1, or it could be defined on the raw descriptors as well. We also consider two other descriptors, which are sequential. So either do smoothing or we do a delta descriptor. So here we have results for 3 different settings. We were testing here day versus night scenario. And for example, a model trained on Brisbane is tested on Oxford, and a model trained on Oxford is tested on Brisbane. We found that one of the limitations we knew for delta descriptors was that for short sequences, it may not work that well. And that is what we found here in most cases. And that was also the motivation of coming up with SeqNet, where we use just a short sequence of 5 frames, and then we're able to supervise it to learn a better description of that particular place. So in most cases, we found that the green lines, which are mostly SeqNet-based methods, they tend to perform better than other options. So other options being smoothing, delta, or single image-based systems without any further training, they typically tend to underperform. This test we did to check whether the system generalizes across different seasonal variations. So if we train on summer versus winter scenario and test it on spring versus fall scenario, we still are able to show that the system still generalizes and it learns certain temporal dynamics that it is always able to perform much better than other methods. The third one was on mapillary street level sequences. These are highly dynamic conditions. For example, images are captured from different cameras, different lighting conditions, structural variations, and there are these roadworks or other things which are happening. So, and the data itself is like training on Melbourne and testing on San Francisco. Citywide changes are quite large. So all this, so this makes this problem relatively harder. You'll see that the recall values as such are typically low for, absolute values are low as compared to other data sets. And this still remains a challenging problem. These are some additional experiments, for example, comparing different method types. So this is a taxonomy based on what different types of methods exist. For example, single image based techniques, we have a few different options here. And we found that there is no one clear winner across all of them. So they all have their own properties. And this makes it interesting that with SeqNet, we can actually include any of these descriptors. For most of our experiments here, we use NetVLAD. But for example, DenseVLAD, which performs better, so that could also be used with these to even improve performance further. In sequential descriptors, SeqNet performs better than delta or smoothing. And in sequence score aggregation, there are these methods GISM, GRH, which are existing state-of-the-art methods. They use sophisticated sequence search techniques, and we club that with SeqNet S1. But we found that just using sequence matching with SeqNet S1 tends to perform better. Similarly, hierarchical options which we considered. So the S5 to S1, this is the final one which we used. So that is better than the other ones. There was an additional experiment which we did with the reverse traversal. So here what we did was the database was indexed in a reverse order because we wanted to test like what all methods would break if we reverse the sequence. So because delta is a direction-based difference vector, so that would suffer more, but smoothing being an agnostic method to the direction bit. So smoothing doesn't get affected and performance is still high. Sequence matching. So sequence score aggregation wants to find matches across the main diagonal. But if you have reversed your database, then it would mean that you want to find matches on the off diagonal. So that's why we consider reverse sequence matching here as well. So if you have reverse sequence matching enabled, you can further improve performance. But what we wanted to see was like how much the method is actually order dependent. And we found that SeqNet S5, it's not that much order dependent, and it is still invariant to some extent to the changes in the order. Another important question is the length of sequence. So how do we decide what length to be used? So that remains a system parameter. And it is known that if you use a longer sequence, it is likely to improve performance. And as compared to an existing state-of-the-art method, we show that even if we increase the sequence length, so in this case, we fix the sequential descriptor length to be 5 for all these cases, but we increase the sequence score aggregation length to 5, 10, or 20. And we find that performance keeps on increasing, but it is still better than the existing method. Yet another experiment where we looked at another descriptor. So what if we use, other than net, we'll add some descriptor which is rather weak. So GMP is a global max pool vector, but it is not trained for place recognition. And we find that it actually works better. So this means that single image descriptors can have different responsiveness to sequence matching or sequential descriptor learning. So this is an interesting behavior because even if someone optimizes for single image descriptors to perform really well using NetWLAT, even another descriptor which is not really optimized for single image descriptor might perform better for sequential dynamics. So computation time was a big advantage for our proposed method. So we, instead of matching all the images by sequence code aggregation, we only do top 20 because this is an hierarchical approach, and that reduces the computation time significantly. And at the same time, it improves performance. This one is a visualization of the latent space, although speculative. What we found was that with SeqNet, typically small segments were formed. So here the color represents the index of the image, and this is the continuous traverse. So one would want that those indices which are closer, that is the color which have the similar color, they are close to each other in the representation space. We're using t-SNE here. And for SeqNet, what we found was that all these descriptors, they tend to have small segments and are neither very tightly packed as compared to delta, nor very loosely packed, or did not have long segments. And this is by performance performing better than others. So this is just an indicator.
Yeah. So how are we judging the closely packed or loosely packed situation here? I do not understand.
Yeah, so that is why this is a bit speculative at this stage. So we just wanted to visualize how these descriptors, because it is hard to know what is really happening in the high dimensional space. So by performance, we know that this one turns out to be better than others. But still we see that there are some sort of clusters which are visible in all the other ones. But by speculation, we're just saying that maybe tight packing is not relevant. That's why it doesn't perform that well. And maybe loose packing, but with long segments, that is probably also not relevant. So that is kind of, so that's like a reverse understanding of that thing.
So we are deriving the
Hi, Shambhavi, can you hear me?
No, I think there's a connection dropout, but I'm able to hear you at least.
Okay, all right. So we'll just probably wait for to come back.
I'm sorry, my network dropped, I guess.
Yeah, no worries.
Yeah, so we are deriving the conclusion about the visualization of latent space based on the results.
Yeah. Right now, that's what we're just trying to see. So it's not directly, we cannot directly interpret like what's really helping the system to really perform well. So this was more of an analysis than like it's still qualitative, I would say.
Understood.
And there could be other ways like maybe not TSNE, but PCA visualizations might help here. So that's something which is still trying to understand and explore.
Mm-hmm. And there was one more question I had in middle of the your presentation. That was, can you really reason out how is contrastive learning so helpful in this particular use case? Like I've seen working it out a lot for medical imaging cases. We have hosted talks about those papers. How is it helpful in this case?
So I think just in case of representation learning, if we try to do it other way, let's say by classification or something, so then the interactions between different elements, that is not at focus. So then what system tries to do is that it independently tries to optimize a particular value for a particular class, let's say. But in case of representation learning, we are constantly comparing all the descriptors with each other, and then trying to optimize that, okay, a descriptor has to be this much distance away from that one, this much distance away from the other one. So then that packing of that whole space is being optimized, rather than saying that, okay, it might be possible that distance between two different elements for classification would be very small, because that is not something we are optimizing for, but you could still be able to predict well during training or even during testing. But here the focus is to actually learn representation based on this whole phenomena of pushing and pulling the distances between different elements.
Yeah, understood. Sorry, I was on mute. Thank you.
So Saurav, I had a quick question actually. So yeah, how robust are your descriptors? Because if I see in the if there are people moving in, so is your global descriptor that you're trying to extract for an image, or does that have an influence on it? Because at different times people will be different. Of course, the places might be constant. Does it have an influence on it, or is there something which you have already told? If I'm sorry about it, in some other form, maybe if you can throw some insights on it.
Yeah. So I think that is definitely one important problem. Like, how do you deal with dynamic objects, which obviously keep on changing, and then you have to always estimate that there is an object and then somehow ignore it. So that is what single image descriptors try to do. Like when you're learning that behavior, so that is what has been shown in the existing works, that when you're learning a representation of single images, then ultimately the system learns to ignore cars or pedestrians and these things which are not relevant. And it focuses a lot on buildings because they're trained for urban city environments. So that is how like it relatively weighs different elements of the scene to then perform better. And in this case, because we're only dealing with sequential aspect and the underlying descriptors already learned those properties of ignoring pedestrians and all. So right now that is not a problem here. But if we were to do it end to end, then the system would have to optimize for both the things.
Okay. Is there some way on how are you saying that, okay, it's trying to focus only on the buildings but not the pedestrians or the other dynamically moving objects? So is there some way that you are trying to say this, or is it through results that are shown in the existing works that you are saying?
So with images, it is relatively easier because there are existing techniques which we can use to then let's say what typically is done is you mask certain parts of the images, and then you look at how your descriptor changed.
Okay.
And
Okay.
with that, you can say that, okay, with this part occluded, my descriptor changed so much that it started giving errors. So that visualization can be done in the image space. So like for example, the NetVR descriptor which we are using, so in their paper, they have these visualizations which they show that this is what the network has learned based on the activations what they get.
Okay. Okay. Thank you so much, sir.
Nice. So in conclusion, sequential imagery, we know it is helpful for place recognition tasks, but it can be used in various different ways. For example, sequential descriptors, as we proposed, and some other recent works have also done that. Match score aggregator, which is a more well-known method of using sequential information. And then there's the hierarchical combination, as we did in this work. So learning sequential descriptors over short sequences via SeqNet, we found this to be a more informative option than independent collection of single descriptors. So having a single sequential descriptor is much better, more robust. It reduces latency because we're able to do that with a short sequence instead of using longer sequences as many other methods do. We compared with those methods and found that our method still performs well. It reduces compute time because with a representation which itself has sequential information, we can use approximate nearest neighbor searches to quickly find what those top matches are. But even if we brute force search for them, we can then plug sequential descriptors into hierarchical pipelines. And then instead of doing sequence code aggregation for the whole database, which we showed that would take much longer to process, with the hierarchical approach, it becomes even simpler, and it at the same time improves performance. So in future, we are right now working on putting up an end-to-end pipeline. So there we can learn both the single image descriptors and learn these temporal dynamics together. And then we have this idea of improving the responsiveness of single image descriptors so that we optimize for match score aggregation directly. So the loss function here would change. And then we also found that although we observed generalization in several different cases, like across different conditions, across different cities, so we have several experiments for those, but there is no single model which would perform well across all the conditions, which is often a problem in many machine learning problems anyway. So one thing which still remains is a large scale training, which considers both spatial and temporal aspects together. So that still remains as a to-do thing. So to know more and to connect, you can look at the GitHub Scholar or connect with me on Twitter or LinkedIn. So that's all from my side, but if you have any questions, you can ask me now or even later.
Hi, Sourav.
Yeah, that was okay.
Yeah.
Nikhil, please go ahead.
Yeah, I have a question. That are there any unsupervised or self-supervised learning approaches to this problem VPR task? Because, for instance, let's say we can use Google Map information to take the places and their corresponding images and try to build a system on top of that.
Yeah. So typically, what like a you can call it partly self-supervised because GPS information, and like you said, that Google information from Google Maps. So that is all easily available. So most of these systems which are trained, so we use GPS information to then get those images from the same place and then train the system, because then so the ground truth is quite easy. But theoretically, it is not self-supervised, but there could be ways. For example, for temporal systems, you can always say that images which are close in temporal axis to a particular image, they should be matched with this one. So that could be a method which does not use any kind of GPS information. So that could be completely self-supervised. But again, there could still be some challenges. The other option is to use some sort of pre-training. Like these days, there are some evidences that if you pre-train on a large enough data, then you do not need any kind of supervised training systems. So many self-supervised or pre-trained systems on a large corpus of text plus images have shown to outperform like previously existing supervised methods. So those options might still be there.
Yeah, thank you.
Okay, great. You can pitch in your questions whenever you guys are ready. In the meanwhile, I have a few questions. So there are a lot of questions regarding how the paper started and got published that viewers generally want to hear about so that they can relate, and it can help as a motivating factor when they are struggling with their own papers. So
Right.
how long did all of this took, like from the scratch till finish?
So it was kind of related to what we were already exploring. So the initial idea, which when we started looking at sequential information, so one work which we did at ICRA that was looking at how you can use sequence matching pipelines and single image descriptors, but do that for 10 million size reference database. Then we realized that that there are approximate nearest neighbor search methods available for single image descriptors. But the same thing cannot be done for this sequence score aggregating techniques because there is no representation to search quickly for anything. So then this idea came up that maybe we should have sequential representations. And there were some existing works, but they were not really considering this problem from this particular aspect. Then we initially just did some visualizations, and that is what I showed you with delta descriptors. We realized that this is something which can be fixed. We tried some very simple things like averaging, computing differences. So these things, when we tried one of these methods, we came up with then delta descriptors, which we found to work well, but it had, like one of the particular limitations is having a relatively high latency. So we fixed that with this particular work where we had low latency, but this time we also use a supervised technique with this contrastive learning framework to rather come up with sequential representations for a low latency system. So this was more of like a step-by-step thing. So it kept on evolving, I would say. But as such, whether or not something works or doesn't work, that is never in our hands. So, so we try things and it sometimes works. Sometimes it needs more insight. So then we go in, debug, go to the depth of it, see where exactly it is failing, whether what we think it should be doing, whether or not it is doing that. If it is not doing the same thing, same results we don't get, then debugging helps, and then you get more ideas. Okay, so this is the problem I've understood, and now what method I can devise to improve this.
Right.
So I think that's a constant pipeline.
I got it. So basically, if I would be asking that what inspired you, then that would be your previous research work that you were continuing.
Yeah, so it is definitely that evolution of things which gradually came to this point.
And did you have to develop any new skills to work on this problem, or no? Wasn't that?
So I wasn't using PyTorch before. So I started using PyTorch just with this particular work. So that I would say that before that I was more experienced with TensorFlow. And since the community moved on anyway to PyTorch, so that was a high time. So I think that happens all the time. So there are always new things which one might have to look at and understand to do better. And I actually found this to be much more easier than TensorFlow. So which is kind of, I would say, a skill added to my list.
Now you're giving me a lot of positive hope. Currently, I'm also struggling to moving into PyTorch, and there's this guy on YouTube called Aladdin Pearson, not very well known, but his tutorials are so good that they are just the lifesaver for me right now. But yeah, I'm finding it tough to move to.
Yeah, I
But
think so there's always there was always an initial learning curve, but I think you'd be happy with it. And now I've already been seeing people giving these strong arguments that why people have not moved to JAX. So, so I think yeah, maybe you could consider that you could directly jump to JAX than going to PyTorch.
Right. So another question would be, what do you think about reproducibility of the codes? What I have been discussing lately with my fellow people into research is that even when the code is available on GitHub, if you're trying to reproduce the results, sometimes we fail. Like the authors are promising a 95% result, but when we are trying to reproduce it on our own cells, it is around 90, and we can actually not work in that direction further before finding another ways to support our claim or modifying the approach a little bit, because the authors have already promised it, the paper has been accepted. And do you align with this thought process? That
Yeah, I think it can happen. Like reproducibility is definitely an issue. So sometimes it is actually challenging as well to provide the whole thing so that everything is reproducible. But as such, like if some code is released, especially when it is related to training and network and all, so there are sometimes these challenges that these libraries themselves might have some stochasticity and it might be hard to reproduce exactly similar results. But I've seen, in my experience, I've seen repositories where they provide enough support to actually replicate all the results. And with tools like Conda, it is typically, or even Docker, so one can recreate the same environment. So which means all libraries and everything is the same. So as if you have made everything the same, then chances are reproducibility should be really high, unless there was some sort of stochasticity in terms of training and testing. So with PyTorch, I know that if I fix the seeds, I can repeat every experiment exactly in the same way, unless I've changed the code. So if the code has changed, then obviously things might change. But yeah, but I understand, like if it is not reproducible, it can be a problem. But yeah, I hope people like reproducibility is something which would be fixed easily from like it's getting better.
Yeah, it is. That is why we're getting so much faster results nowadays.
Yeah.
Because, yeah. So another question would be, how did you end up choosing this particular domain of research? Were you into it since your master's? Did you explore it on your own self, or just most of the speakers we've hosted so far were into their domain because the supervisor was into that domain?
Okay. So I actually started working in robotics when I was doing, like for my bachelor's at Thapa University. I went into TCS research there. At the time, I didn't make a choice of going into robotics. So that is what they allocated me for. And I was happy to do that. Well, I was working on object detection and tracking. And one of my colleagues, he was working on place recognition. So I was aware of this particular problem. So when I applied for PhD, I knew this is what I was going into. So we started doing place recognition research, and then most of the ideas, like whatever research I've done, so they were I was like always comfortable with them. So some of the ideas my supervisor would throw at me, and sometimes we'll discuss. I would come up with some ideas, and it just gradually evolved, I would say. So it was. Yeah, so like I don't think there was a case when I would not have wanted to work on something and was just working on it for no reason. So
That's interesting. Another last question from my end would be, most people around me who want to get started, like this paper, place recognition paper, is more of the computer vision side of robotics.
yeah,
So I could understand it, and we can try it on our own also if we have the
yeah,
suitable machine. But people who want to get inducted into robotics face this initial hunch of not being able to access the basic people suggest them that you need to work with robots, try experimenting with a robot first, a very
yeah.
basic robot with some motors. How do you suggest, like, can one actually try robotics as an independent researcher, or is an association with a lab necessary?
Yeah, that is definitely a very big challenge right now. So like there are these, I recently saw a post from someone on LinkedIn where the person bought NVIDIA's robotic kit to start with these things. So I think those are the options, like otherwise Raspberry Pi based. But again, like I think with Raspberry Pi, again, that you have to still come up with a moving thing. So that, yeah, that remains a challenge. But I know of some solutions recently which have come up where people are able to look at some very small scale devices and then do some sort of automation on that. So there is a little bit of a deterrent there for robotics. For like perception is one of the main parts of this whole robotic ecosystem. So that's why from research point of view, one can still do some research, especially related to, let's say, perception and navigation, where you are doing that for the application for robotics. but maybe not directly deploying it. But I would hope that this becomes easier in future. But I agree that this is not right now a solved issue.
Right. I was trying to explore social robotics a little bit, but then gave up because of these situations.
Yeah, especially for social robots, maybe it would be very expensive to start with something to just experimenting your own.
Right. Okay, great. That was a great talk with a lot of back knowledge, covering all the basics of the domain, getting into place recognition, covering important papers of the domain and different approaches that exist. Do we still have any question from the audience?
Yeah, I have one.
Yeah, sure.
Yeah.
Hi, Saurav.
Yes,
So
Chandra.
first of all, it was an amazing presentation and the visualizations were awesome. So I had one doubt regarding the generalizability of the system of the
Yep.
SeqNet. So when you showed the results in which the query sequence was in the reverse direction,
Yep.
so how did the system adapt it to work on this? Like if you have the query in the reverse direction, whereas the reference is in the you would say the forward sequence, then in the first step itself, when you are finding out the top matches, the system would fail, right?
Yeah, that is what we were actually looking at with this experiment. So we didn't, sorry, we didn't directly train it for that particular scenario.
Mm-hmm.
But because the way it works is it's kind of a weighted average across the sequential information, across the sequential axis. So that means, but it is not a direct average. So it's a weighted average. So by definition, it does not have a strong order enforced within the sequential descriptor. So if you look at RNNs, so RNNs would do state estimation, and then they're strong. They would have this strong connection of what comes next based on what you have seen before. But in this case, with temporal convolutions, that is something which depends more on the data. So if your data had that kind of a thing, so there is no definition in there which would enforce that order for sequential descriptor in this case. But if it were to be, let's say, RNN or even just concatenation of descriptors across a sequence, so that is again a strong order enforcing setup. So what we found was that there was this limited robustness to order variations. So even if the order has changed, so SeqNet doesn't really suffer here, but delta does, because we know by definition the sign of delta would change because it is a difference-based descriptor. So that is what we found. And for sequence matching, again, if you just do vanilla sequence matching, searching along the main diagonal, so performance is poor because you can't find matches along the diagonal. You'll have to reverse do that matching also in a reverse manner. So then that is definitely is not known. So you need prior knowledge to enforce this. So you need to know that, okay, I am traveling in the opposite direction or the database has been reversed. So that was just to show like how much the performance changes with these different settings.
Okay, understood. Thank you very much. Also, previously you mentioned that you were working as a researcher at TCS.
Yep.
So was it the research and innovation department? Because I've
Yep.
recently accepted in the, like I've got a position in the department.
Oh,
So,
great. Yeah.
Yeah. So I wanted to know how's the work culture there and how's the projects and everything.
Yeah, I think it's
Can
great.
we have that over the recording?
Yeah, sure.
Yeah, so I think work culture is great there. So I was working at the robotics lab at TCS Innovation Labs. So there, the robotics lab had just started there, and I was also aware of the other data science lab. So people usually used to love that kind of experience there because you were allowed to publish, which helped me get into my next step of PhD. Otherwise, those options, if are not there, then that might not make your research effort that much enjoyable. So from that point of view, I think that independence actually helps.
Yeah, sure. I would ask this question personally later.
Yeah, no
I'll
worries.
push it into DMs.
Yeah, that'll be fine.
Great. I guess no more questions. Great. Thank you so much, Saurav. That was a long talk. We took a lot of your time, more than an hour.
Yeah, no, that's all. That's all right. I hope this was helpful and
Yeah,
would be useful for you guys.
definitely. Lot of insights into the domain. I didn't know it could be so interesting, and I definitely didn't know that contrastive learning had great impacts in place recognition as well. I was
Yep,
limited to my understanding that it was doing great with medical imaging stuff, but
yep,
okay,
yep.
promising. Yeah, great. We look forward to more work from you. Thank you so much for accepting my
Yeah, thanks
invite.
for hosting me. Thank you.